So, then this calls for the equation, governing equation at the interface, which is nothing but rho A V A equal to, instead of rho V, now I write rho A V A Y A minus rho D A B dy A by dx. So, this is the equation I have. So, now I can separate the variables like this, rho A V A, see, steady evaporation. That means mass flux of A, that is rho A V A, is constant. Similarly, I also assume the product of rho DAB as constant, because theoretical analysis, some simplification we have to make. So, first one is steady evaporation. So, that means the mass flux is constant, steadily it evaporates at the same mass flux. Second one is, to simplify the process, I take the product of rho into DAB as constant. Now, I can say this rho AVA is constant, rho dB is constant, that into dx equal to separating variable dya divided by 1 minus ya. So, this here I can write rho AVA into 1 minus ya equal to minus rho dab dya by dx. So, now this I separate like this. Okay, now this I can integrate. When I separate this, I can integrate. But let us understand about the boundary conditions also. I have told that at the interface where x equal to 0, which is fixed, ya value will be equal to yai. So, now integrate this equation and substitute this boundary condition, then I get an expression for the variation of ya along x. Okay. So, put x equal to 0 here, x equal to 0, I will get ya will be yai, that is what, and it goes along. So, if you want to put x equal to L here, then put instead of x here L, and I will get the value of ya at L. So, this is the profile or variation of ya. Understand, this is vapor A in gas phase along x. Okay. Now, my next, so I have found the profile. So, yai is higher, ya infinity at x equal to L is lower. So, there is a nonlinear variation for this. We have seen, but by the expression what we have derived. Now, my next interest is to find the what is the mass flux of evaporation of A, which is rho A Ya. Now, I can do that. We know that the mass flux of the A will be dependent on the interface mass fraction. If interface mass fraction value ya is higher, then the gradient also will be higher, so that the diffusional transport will be higher. So, mass flux will be higher basically. So, mass flux can be calculated using the boundary condition at the x equal to L. So, as I told you in the problem, so just go back to the figure again, at x equal to L, ya equal to ya infinity. So, that boundary condition I use here, and I get the expression like this, rho A Va equal to rho dab by L. See, from this expression I find rho A Va. So, writing this 1 minus yax divided by 1 minus yai. So, that in the natural logarithm will give you this. So, just use this equation and apply the boundary condition at ya infinity, so that I get, instead of x I will get L, instead of yax I will get ya infinity. So, I get this expression. So, this expression is the mass flux for steady evaporation of a species A into a mixture of A and B, where B is another gas. So, now this can be written as rho dab by L into natural logarithm of 1 plus by. So, now this term in the natural logarithm, this term I write as 1 plus by. That means, by itself can be written as yai minus ya infinity. This is actually delta y in x direction. divided by 1 minus YAI. So, this is called Spalding's transfer number based upon mass transfer analysis. This is mass transfer analysis. So, it is called Spalding transfer number, very important. So, the mass flux is directly dependent on the product of rho and DAB. If the diffusivity between A and B is very high, then you will see that the mass flux will be higher. Then it is inversely proportional to the distance, that means it decreases the gradient, correct. So, the gradient is nothing but YAI minus YA infinity by L. So, if the gradient is, this difference is larger, L is smaller, then gradient will be larger. So, that means more diffusion take place. But in this case, if L is larger, then the mass flux will reduce. So, gradient will reduce. So, that comes in the bottom. Then in the natural logarithm, the By number comes in 1 plus By. So, this By again signifies the gradient of y. So, but seeing the fact that By is in the natural logarithm term, even By increases say by 5 times, we can see that the mass flux will increase 2 times or 2.5 times, that is it. So, basically we can say that the mass transfer is driven by the product of rho DAB and the gradient of the mass fraction at the interface. Okay. So, this is important analysis. So, I can say that I can write rho AVA, which is equal to mass flux of A equal to rho DAB divided by L into natural logarithm of 1 plus By. So, this is the expression I get for the steady evaporation. Now, only considering the mass transfer using Fick's law. So, this statement I have taken and I have given this expression for the mass flux. But there are certain unknowns in this. How will you calculate YAI? YA infinity is fine. So, at the farther distance, based upon the concentration of A flowing along with B, I can fix this value. So, this is known, but this how will you fix? This YAI depends upon the surface temperature. Surface temperature depends upon the heat transfer from the gas phase to the interface and interface to the liquid phase, correct. So, the heat and mass transfer are coupled. Okay. So, to summarize, mass flux of the vapor from the interface is driven by the gas phase conditions because of the gradient. So, if more concentration of YA flows above the beaker, then YA infinity value will be higher, so that the gradient will be lesser. So, that means you will not have much more mass flux. But if YA infinity tends to 0, then you will have more mass flux. This means that the gradient of fuel mass fraction at the interface dictates the mass flux along with the property rho DAB along with this. So, now if the vapor which is formed over the liquid fuel surface is transported at a faster rate, that is, it is removed, then the gradient of the mass fraction of the fuel will become higher. That means more mass flux will generate. But if you do not remove it, if the vapor accumulates over the liquid surface, then the gradient slowly decreases, so that the flux also decreases. So, this means that how to remove the vapor accumulated at the faster rate? You have some convective flow on the top, like the flow of gas A and B in this case. So, evaporation in a convective condition will enhance the evaporation rate. Now, we will do the same exercise of what is the mass flux during steady evaporation, but now using the energy balance. For that, I consider the basic heat equation in a differential form. There is no, it is a steady. So, that means rho Cp dt or dou t by dou time, this is 0, no source terms. Okay. There is nothing will increase or decrease the temperature in the gas phase. So, no source terms. So, S equal to 0. So, that means I have convective term and the conduction term or diffusion term. So, these are the two terms in the governing equation. M dot is nothing but rho V, correct. Cp is the mixture's specific heat at constant pressure, dt by dx, because of the fact that it is only one dimensional and time derivative is also 0, the partial derivative is written as ordinary derivative. So, rho V Cp dt by dx equal to kg into d square t by dx square. That is the governing equation. And this mass flux rho A Va steady evaporation, so this is constant, and kg is the thermal conductivity of the gas phase mixture and Cp is the specific heat at constant pressure. Obviously, we will use for theoretical analysis properties are constant, kg and Cp are constant. Now, I define Z I define as Cp by K, G. Now, this equation I integrate so that I get this. Second order derivative becomes first order derivative and the first order becomes the algebraic equation like this. So, dt by dx equal to Z, which is Cp by K into m dot double dash into T plus C1, where C1 is the constant of integration. Now, this is one equation I am getting. Now, I can separate this equation. So, dt by Z m dot double dash T plus C1 equal to dx. So, I separate the variable and integrate again. To understand? So, first I integrate this and get this. One constant has appeared. Now, separate this and integrate again. Second constant has appeared. Correct? Now, I get the expression like this. Now, there are two constants of integration, C1 and C2. So, we need to apply two boundary conditions. So, let us first apply the boundary condition at x equal to L. So, what happens in this? So, this is the steady evaporation. So, this is x equal to 0, this is x equal to L, and here T equal to T surface and here T equal to T infinity. That is the case here. Obviously, T infinity should be greater than Ts for the heat flux to come in. So, this is a liquid A. So, this is a Stephan problem, same problem. So, now we can see that at the end of the beaker, we approach the infinity. So, the boundary condition there will be x equal to L equal to T equal to T infinity. So, apply that and get one constant. Similarly, at the interface, x equal to 0, T equal to Ts, that you apply. Then you will get two equations with two constants. These two constants can be now evaluated by solving these two equations. And finally, I get a expression for T. Do you understand? So, it is very simple. Governing equation is taken, integrate once to get this, one constant of integration appears, separate the variables again and integrate, two constants are appearing. To solve these two constants, I need two boundary conditions. One boundary condition is that the interface x equal to 0, T equal to T infinity, Ts, x equal to 0 interface, T equal to Ts, x equal to L for go boundary, T equal to T infinity. Now, apply one by one and get two equations. Say this is equation 1 and this is equation 2. Simultaneously solve these two equations and get the values of C1 and C2. Now, when you get the solution, I am interested in temperature, correct? So, find a temperature profile at any x, you get this. So, now if you supply the value of x here as L, then you will see that you will end up getting T equal to T infinity. If you put here 0, then you will get T equal to Ts. So, this is the expression, so you can check this. Looks like complex equation because of some exponents etc. appearing, but it is very simple equation. So, if you can check the boundary conditions, verify them, put x equal to 0, you will get T equal to Ts, x equal to L, you will get T equal to T infinity. and this is called temperature profile in x direction, where the temperature actually varies from T infinity at x equal to Ts. Okay, now to find the steady evaporation rate, now again we will revisit the interface boundary conditions what we have. That is a heat transfer from the gas phase to the interface. Part of it is given from interface to the liquid phase and part of it is fed for evaporation. So, this is what I get, correct. So, now when steady evaporation occurs, the temperature here, surface temperature becomes almost constant. So, that is this will tend to 0 when steady evaporation occurs. Initially, the liquid phase, it is gas phase. Liquid phase may get heated up, but once the surface temperature reaches, so that means when liquid phase is getting heated up, the surface temperature slowly increases. But once a steady evaporation condition is reached, then the liquid phase temperature or the surface temperature will eventually become constant. That means the heat transfer from the interface to the liquid phase tends to 0. In that case, the heat coming from the gas phase to the interface will only supply for the vaporization. So, K, and this heat transfer from the gas phase to the interface comes through conduction, that is Kg gas phase, this is flux, heat flux, Kg gas phase thermal conductivity into the gradient of the temperature at the interface x equal to 0, that will be the heat flux. I will say Q dot double dash G to I, that is the heat which is coming in, that will be used for evaporation. M dot double dash, both sides I am dividing by area, M dot double dash into H of G. So, this is the boundary condition or the energy balance when steady evaporation occurs. We have seen the fixed law. Fixed law, this mass flux equal to rho A Va is constant, which is equal to rho A Va Ya plus rho Dab Dya by dx. So, this is the mass transfer statement, this is the heat transfer statement. Okay. So, for the heat transfer based analysis, I use this condition, which is the interface condition for the energy balance. Why? Please understand that the liquid phase heating is now absent because of the fact that Ts has reached a constant value, almost constant value. Okay. Now, this temperature profile is available. Now, from this I can find dt by dx and put x equal to 0, which is to be used in this equation, correct. See, I need the gradient of temperature at x equal to 0. I have the temperature profile itself evaluated from by solving the governing equation. Now, from this find the dt by dx value and put x equal to 0, I get this value. Do you understand? So, z m dot double dash T infinity minus Ts e power minus z m dot double dash L divided by 1 minus e power minus z m dot double dash L. So, that is the gradient. So, now I can substitute this gradient value to this and find m dot double dash, that is what I need. So, I get this m dot double dash h of g equal to k into this is what dt by dx, which I have found from the temperature profile and put x equal to 0 there. So, now please see this equation has both sides m dot double dash. So, now try to do some algebra and simplify, I will get the expression in a very simple form. M dot double dash equal to kg by Cp. Understand? Z is defined as Cp by kg. So, now I also use Z as Cp by kg. Now, I get the expression Cp by kg, now 1 by Z will appear. So, it is kg by Cp, 1 by L also comes into natural logarithm of 1 plus Bq, where Bq is the Spalding transfer number based upon energy equation. So, Q comes as a energy term there. That is nothing but Cp into T infinity minus Ts by h of g. So, this is the what this is. This represents the heat transfer from the gas phase to the surface. This is the heat required for vaporization. So, the Spalding's energy transfer number will be the ratio of heat transfer to the surface divided by the heat required for vaporization. So, I will write m dot double dash equal to kg by Cpl into log of 1 plus Cp T infinity minus Ts divided by h of g. So, this is the expression I got. Previously, I got another expression rho dAb by L natural logarithm of 1 plus YAI minus YA infinity divided by 1 minus YAI. So, this is the other two expressions. Please understand that this is a steady evaporation. So, the expression for mass loss rate or mass flux from the interface based upon energy equation or the mass transfer equation should be the same. Okay. So, to summarize, mass flux from the surface will be equal to rho dAb by L natural logarithm of 1 plus By, where By is this YAI minus YA infinity by 1 minus YAI will be equal to kg by Cp into L natural logarithm of 1 plus Bq, where Bq is Cp into T infinity minus Ts divided by h of g. Now, these two should be equal. Now, I define what is called Lewis number. What is Lewis number? We know that K divided by K, here actually this should be K is the thermal conductivity, or Kg divided by Cp rho dAb. Okay. So, K by rho Cp is alpha. So, Lewis number is alpha by d, that is it. So, here I am saying K rho, bring it here. So, this will be alpha by d. If I take LL cancels. So, alpha by d is what? Alpha by d is Lewis number. So, 1 plus B, this is actually BQ, 1 plus BQ power Lewis number I take in the natural logarithm. So, what I get here is natural logarithm of 1 plus By will be equal to Lewis number into natural logarithm of 1 plus BQ. Okay. So, now this I take to the, so 1 plus By will be equal to 1 plus BQ to the power of Lewis number. That is what I get here. By equating these two, I get only this expression. 1 plus By will be equal to 1 plus BQ power Le, that is Lewis number. Lewis number is defined as K by rho dAb Cp. Okay. Now, this is the coupling. How to solve this problem? To get the values, first of all, there is a fixed ambient temperature. Now, based upon the ambient temperature, when the steady evaporation takes place, a equilibrium surface temperature is attained. Ts will become constant. This will be close to the saturation temperature or the ambient temperature. Okay, if so, this is saturation temperature, or you can say or ambient temperature, whichever be the lower value, ambient T, whichever is lower. Okay, that means if T infinity is more than the boiling point, then Ts will reach the boiling point temperature. If T infinity is less than boiling point, then Ts will approach T infinity, not the boiling point. That is, you have to understand this. So, now how to find YAI? Once Ts is known, I will use an expression like Claussius Clapeyron equation to estimate the mole fraction or partial pressure of the fuel vapor interface. Once mole fraction is got, then I will get the mass fraction. Okay. So, this is the procedure to be followed. So, what we do here is, we take a surface temperature value and try to calculate the mole fraction based upon Claussius Clapeyron equation, then find the mass fraction and substitute here and see whether this equation is same or different. So, let us illustrate it more. So, from this equation, from this equation, I can elaborately write for By and Bq and get this equation, correct. So, this is actually 1 plus Bq power Le. So, this is 1 minus Yai divided by 1 minus Ya infinity. So, that I have written like this. So, I am trying to find Yai as a function of this Bq and Ya infinity, where the Bq, the main variable is Ts. This is what is known to me. Okay. So, when you fix T infinity is fixed, Ts can be determined as a function of T infinity. Okay. So, now let us analyze this equation. It is clear that when T infinity tends to infinity, this T infinity is higher and higher. So, 100 degrees, 200 degrees, 1000 degrees, etc. Then Ya will tend to unity. That means partial pressure of the vapor will set to 1, go to a value of 1. Or if latent heat tends to 0, that means you operate at higher pressure, etc. Latent heat tends to 0, then also Yai will tend to 1. So, in fact, Yai is a strong function of Ts, correct. So, Ts approaching the saturation temperature or boiling point, Ya approaches 1, that is the thing. So, now this is equation C. So, I can solve the equation C for a given value of Ts and find the mole fraction of the A at interface using, say, Claussius Clapeyron equation, which is written like this. It is nothing but the P sat by the total pressure P equal to exponent of minus HFG by R. This R is the specific gas constant. Of fuel, say A, okay, into 1 by T. T is any temperature, it may be surface temperature, divided minus 1 by T boil. Please see, if surface temperature, this is surface temperature, approaches T boil, then XA will be equal to 1. That means Ya also will be equal to 1. Okay. So, that is what we are trying to say. So, what is the procedure to solve? I will get the value of T infinity is fixed. Now, I will take a value of Ts, find Xai, then find Yai and substitute here and see whether this equation is balanced. If not, I will change the value of Ts. Okay. So, that is what illustrated in this procedure here. First, I assume a value of Ts, then I use this equation D, which is Claussius Clapeyron equation, to find Xai, that is the mole fraction of A at the interface. Then I find the mass fraction. So, mole fraction, mass fractions are used. Okay. Then I go to calculate Bq and By. So, Bq is this, By is this, when you arrange this in the other way, then equate them. If, or you can substitute in the equation C and say whether the equation is satisfied. If equation C is not satisfied, then the value of Ts is adjusted. So, you will get finally, for a given temperature T infinity, I will get a particular value of Ts, which can be either close to T infinity or close to boiling point. Okay. So, if T infinity is greater than T boiling point, then Th approaches T boiling point. If T infinity is less than T boil, then Ts approaches T infinity. Okay. That is the context here. So, in the way you determine this, do you understand? So, the mass transfer and energy transfer both leads to only one particular equation for mass flux, steady burn evaporation mass flux, and here the surface attains a equilibrium temperature based upon the value of T infinity. If T infinity is increased, surface temperature also will increase. So, when T infinity is greater than T boil, surface temperature approaches T boil. If T infinity is less than T boil, surface temperature approaches T infinity. So, this is the procedure to follow to find the interface quantities.